you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with a tutorial on probability and statistics. Today is the first of a three-part series, and today's focus will be on probability. When we are working on probability, we are calculating or determining how likely it is that something will occur. Important part to remember is that if something is certain to happen, it has a probability of 1, or 100% if we are expressing our probabilities as percentages. Something that's impossible to happen is said to have a probability of 0. Everything else is likely to be in between, so it can possibly happen but not guaranteed to happen, and it will have some probability between 0 and 1. So you can see here, the bigger the probability, the more likely it is to happen. Now we can determine probability experimentally or theoretically. When we do an experiment, we run the experiment some number of times, and we're looking for some particular event called E. So we would count up how many times that event or action occurred divided by the total number of trials. On theoretical, we have to determine and be able to count how many possible outcomes there are and how many possible ways our event can happen and do that division. As we run an increasing number of trials, our experimental probability should and will approach our theoretical result. Another important thing is that if we know the probability of some event happening, the probability of not that event happening would be 1 minus the probability, because something either happens or doesn't happen, and the total probability has to be 1. So in rolling a die, we could do both experimental probability and we could do theoretical. So let's say we had this example, we rolled the die 12 times and we got this series of numbers. And we wanted to determine what's the probability of getting a 3. So based on this experiment, we got 3 3s out of the 12 rolls. So we have a 1/4 probability, or as a decimal, 0.25. Now theoretically, we can do theoretical probabilities on a die. There are 6 sides, and we can assume it's a fair die, meaning each of the sides are equally likely to come up. So there are 6 sides. Only one of the sides has a 3 on it, so we have a 1/6 probability, or about 17%. So in this case, we had a higher number of 3s than expected, but if we would keep rolling and rolling, eventually this number up here would converge onto that number. When we are determining theoretical probability, we have to be able to count the outcomes. We could try making a list or a table. A frequent problem when we are working with probability is rolling, say, 2 die. So if we wanted to know the probability of rolling a sum of 6, we need to look at all the ways that we could get a sum of 6. One way to work that out to make sure we don't miss any combinations would be to make a table here. So this would be, say, the first die and its possible outcomes, the second die and its possible outcomes, and then we have filled in at the intersection the sum of the numbers. So this is 1 plus 1 gives us 2, 1 plus 2 is 3, etc. Now if we wanted to know the probability of getting a 6, we can count the number of 6s in the table, 1, 2, 3, 4, 5 6s, and there are 36 total combinations, so the probability would be 5/36. We can also make a tree diagram. So we're looking at the probability of getting so in this case we're rolling, say, a single die and flipping a coin, and we're looking for getting a 6 on the die and a heads on the coin. So if we made a tree diagram, the first thing we would do would be roll the die, and the possible outcomes are listed here. And then on each of these outcomes we're flipping a coin, and can be heads or tails. So we are enumerating all the possible outcomes. So the probability of getting a 6 and a heads, we only have one place where that was true, and there were a total of 12 possible outcomes, so we have 1/12. So let's work, before we go to that, let's work another sample problem. So I've got a problem here where, let's say we're trying to roll, again we're rolling 2 dice, but this time we're going to multiply the numbers on the die, and we want to know the probability of getting an even number. So I made a table here, but now we've got to fill in the product. So 1 times 1, 1 times 2, 3, 4, 5, 6. If we go across this row, we're multiplying everything by 2. And if we go here, we're multiplying by 3. Here we're multiplying those numbers by 4. Now we're going to multiply by 5. And multiply by 6. So again, we have 36 possible outcomes. We're looking for the probability of even. So there were 36 possible outcomes, and the even ones, we have 3 here on this row. All these are even, that's 6. We have 3 on this row. We have 6. We have 3 on this row, and we have 6. So we've got 9, 9, and 9 are 27. Both those numbers are divisible by 9, so we have 3/4 or 75%. Now some of you might have guessed that there was a 50-50 chance of even, but by the way numbers multiplication works out, it ends up being 75% of the time. Now let's look at another example where we could make a tree diagram. So we're going to flip a coin 4 times. So the first time we flip the coin, we could either get heads or tails. On the second flip, this coin could be heads or tails, and this coin could be heads or tails. And here we, again, on our third flip, heads, tails. We have here heads, tails, and heads, tails, heads, tails, and then our fourth flip, again the same thing. Should have spread my tree out a little bit further. So that's a point to learn if you're going to be making a wide tree. Let me see if I can capture some things and maybe move it down. Oops. Nope, I can't do it. So let's go back and not waste time here. So this is heads, tails, heads, tails, and now because I made this so cramped, it's going to be hard to read. Hopefully we won't make a mistake. And then we start following the path. So we have 4 heads here, and we have 3 heads and a tail. Heads, heads, tails, heads, 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 tails, tails, and we would keep going. Now we're looking for, now as we can see, if we count the ends here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes. And if we find the ones that have 2 heads, so 1, 2, that one's 3, 4, 5, 6, 7, not this one. This one does 8, 9, 10, 11, not that one. Not that one, not that one. So I counted 11. I hope I didn't make a mistake on that. So the probability would be 11/16. So we learned a little bit here. We should have started out spreading these out so that we could have made more room. Okay, our next topic is called making a probability distribution. Now you remember from the first slide, if we list all the possible outcomes of something, the sum of all those probabilities has to add to 1. So a probability distribution is a table or graph showing the probability of each outcome. Many times in graphing it, we will assign a random variable to each of the outcomes. So in this case, it would be obvious if we were doing 2 dies, the random variable could be the sum of the 2 dies, so these were the sums. And from that table that we made up earlier, we've computed the probability of each possible outcome. And if you add all those fractions together, we get 36 over 36 would be 1. Sometimes when we plot these distributions, we would plot them as a cumulative distribution. So this would be 1/6, 3/6, 6/6, etc. So then when you do cumulative, these probabilities as they go up are the probability of getting that number or less. So let's make a probability distribution here. We have a bag of marbles. Now this one, we don't have numbers, so we're going to assign, so we've got the marble color. Oops. We've got the marble color, which we could have blue, red. Whoops, that's a red. I'm having trouble here today, folks. And green. And we've assigned those numbers. So blue we said was 1, red was 2, and green was 3. Now the probability of getting a blue, now there are a total of 25 marbles in the bag, so probability of blue would be 8/25. The probability of red would be 9/25, and the probability of green would be 8/25. And we could double check if we add across, we get 25/25 to show that they add up to 1. Okay, now that was the basic probability. Now another basic probability is a geometric probability. In this case, you can think of yourself as being blindfolded and throwing something at a target, say a dart. And we're not aiming, so the probability of the dart landing somewhere inside the target area is completely random. So the probability of getting a hit or success is a ratio of the area. So we find the area of the part that counts as a score, and we divide that by the total area. So if we look at an example, we're throwing a dart at this circular region, so the area in blue here is the entire target, so every dart will hit somewhere in that circle. And we get success if the dart lands outside of this square. So the blue areas are the target. So we need to know the area of the blue part and the total area. Now, we don't have dimensions on this, so this circle has a radius of r. So the total area is pi r squared. Now we need to get the dimensions of our square. So across this diagonal we have 2r, that's an r, so we have 2r for our diagonal. And this side we don't know, x and x, so if we use the Pythagorean theorem we know that x squared plus x squared equals 2r squared. So 2x squared equals 4r squared. So if we solve here for x, we would divide by 2 and get x squared equals 2r squared. And since we'll just go ahead and leave it x squared because the area of the square will be x squared. Now our success area is the area of the circle, which is pi r squared, minus the area of the square, the cutout, the white. So that was 2r squared. So we get pi minus 2. I'm factoring out an r squared. So our probability of success, the probability of hitting the blue area, is the target area, which is pi minus 2 times r squared over pi r squared. And so we end up with pi minus 2 over pi. And I brought a calculator in here and I calculated that and we get 0.363. So about probability of about 0.36 or 36%. Here's a second example, similar to the last. Again, we're looking at the probability of landing in the blue area. And I already have this one typed out. So the area of the square is s squared. So we are labeling the side of the square with s. Using the Pythagorean theorem, we can find the area or and the dimensions of the inside square and calculate, and we end up getting probability of 0.5 because that inscribed area ends up being half the area of the outside. So that's geometrical probability. So again, it's the ratio of the areas. Now sometimes when we're playing a game, we want to know whether it's a good bet or a fair bet. So we can use something called expected value. Now expected value here is using the formula is using this sigma, which in the middle, that Greek letter there called sigma, which is for summation. So essentially what we're going to do is for each possible event or outcome, we're going to multiply the value for that outcome, which is the x sub I, times the probability of that outcome happening. And then we just add all those values up. And we're looking at then the value when we get that and to make a decision on good or fair. So that'll be a little easier if I look at this next example. And before we do that example, we're going to let's talk about this summation notation. So this means we are going to plug I, these values starting at 1 and counting up by 1 till we get to 4, into this equation, and then we're going to sum all that up. So we have to put in values of I equals 1, I equals 2, I equals 3, and I equals 4. So if I put I as 1, I get 3 times 1 minus 1. And now we put in I as 2, and we put in I being 3, and I being 4. And we compute, so this is 3 minus 1 is 2. This is 6 minus 1 is 5. 9 minus 1 is 8. And 12 minus 1 is 11. And we would then add all that up. 7 plus 8 is 15, 26. So again, that's the sigma notation. Okay, let's look at an expected value example. This one's using something you've probably heard about, the New Jersey Pick 6 lottery, or maybe lotteries in general. In this case, you buy a ticket for $1 and you're placing a bet that you will get and match 6 of 6 numbers that you've selected, or you also get payouts if you match 5, 4, or 3. The payouts are shown here. Now, when there's no winners, some of the money that the lottery earns goes back into a pot, so these winnings over time increase. Right now, the winning will be, if you take the cash option, which is the money that you would get in a lump sum, you get 2.7 million if you match all 6, and you get these winnings here. They've calculated for us. We'll learn in a later unit how we could have calculated those odds, but they calculate the probability of winning. And remember, these are the only ways to win. So if we add up those probabilities and subtract it from 1, we would get the probability of not winning anything, or the probability of losing. And I calculated that here and rounded it, so there's a little bit more than 98% probability of losing. Now these are the values of winning the various bets. Now we have to subtract the $1 that we paid for the ticket. So this amount, $2,699,999 would be the value of winning the pick six, all six, and this is the probability. So if we multiply those, we get the expected value contribution for that win. It came out to be about 19.3 cents. This is matching 5. That comes out to be about 5 cents. Matching 3 is about 5 cents, and matching 4 was about 5 cents. Matching 3 was about a little bit more than 3 cents. And again, the rest of the time we're losing 98 cents. So if we add all those probabilities, all those expected values up, we get a total expected value of negative 65 cents. So you can see why this is a moneymaker for the state, because every dollar bet, they're gaining 65 cents. Now, they probably gain more like 50 cents because as there are no winners, they're getting all the money, but they're putting some of that money back into growing this pot. Now, we could get a value here somewhere in the range of $14 million for a cash option here, a 14 million cash option. Now we're getting close to having, or we would have a positive expected value. So if you want to play the lottery, even though there's a rare chance of winning, wait until the pot is up to close to $14 million and then maybe give it a go. But even then, even though the expected value will be positive, there's still a really low chance of winning, so don't go spend all your savings on that. Here's another example of expected value, the insurance business. So in 1996, you can see there were about 125 million cars in the U.S. and a little bit more than 13 million of them were involved in accidents. Now, when you pay for insurance, one of the kinds of insurance is collision, that pays for accidents, repairing your car, and the average premium was $685 per car. And when a car was involved in an accident, the average payout was $2,100. So do consumers or the insurance companies make out? So we can calculate here the probability of an accident by taking the total number of cars involved in accidents divided by the total number of cars. So it's about a 11% chance that the car is involved in an accident. So not being in an accident would be, those two have to add up to a 1 or 100%. So we take the expected value, so the probability times our value. Now when we're in an accident like the lottery here, we would get a payout, but we also paid the premium, so that's our net amount of money if we're involved in an accident. If we're not in an accident, we're just paying out the money, and if you calculate that, the expected value is negative 460. So the insurance company is making $460 profit on every car. So it's not a bad business. So now we've talked about probability of single things happening. Now we need to talk about multiple events. So these are when we're doing, say, one thing like rolling a die, but we're looking for or winning when there are different kinds of outcomes. Now these outcomes could be mutually exclusive, meaning the two outcomes cannot happen at the same time, or they could be non-exclusive, meaning that it's possible for two things to be true at the same time. For example, if we're rolling a single die, the probability, or when we're looking at the number being even or the number being odd, those are mutually exclusive. A single number cannot be both even or odd. This situation is an example of not being mutually exclusive, because if we win if the number is either even or the number 2, well, 2 is an even number, so in those cases both of these things can happen at the same time. This would be another example of mutually exclusive. A number could not be 3 and also be even. Now the reason we need to think about this, the formulas for when we do probabilities are different depending on whether the events are exclusive or not. If we know that two events are mutually exclusive, if we want to know the probability of A or B happening, then we just add the probabilities. So on a die, getting a 1 or a 2 would be mutually exclusive. So to find the probability of getting either a 1 or a 2, we would just add the two probabilities together. Also, in this case, they're mutually exclusive, so we can just add the probabilities. There are situations when they are not mutually exclusive, in which case we need to factor in, because what it ends up when we're counting these cases, we're double counting this case. So if we count the number of twos, there's one, and count the number of evens, there's three even numbers, but we've counted the two twice, so we have to subtract that out. So there's only one case where you're both even and two, so we had to subtract that out because it was being double counted. So ORs typically is, again, an addition problem. The only thing we have to be careful about is this mutually exclusive. So let's look at an example with the mutually exclusive. Now we're dealing with playing cards. Remember, in a deck there are 52 cards, and there are 4 suits. Remember, we have ace, king, queen, jack, and then 10 on down to twos. And there are 2 colors, reds and blacks, and there are 4 suits. So in this case, the probability of being red and or an ace is not mutually exclusive, because we could have a red ace. So the probability of red plus the probability of, that was supposed to be a P for probability here. So probability of red plus the probability of an ace. And now, since they're not mutually exclusive, we have to get the probability of it being both. I don't know why I put that in parentheses there. I'm just really having trouble today. So the probability of essentially a red ace. So the probability of red, half the cards are red, so that's 26 out of 52. And the probability of an ace, there are 4 aces in the deck, so that's 4 out of 52. And there are 2 red aces in the deck, so we have to subtract that. So we get 28 out of 52, which we would then want to reduce. We could divide that by 4, so we get 7/13 as our probability as a fraction. Now, kings and queens, there's not a single card that's both a king or a queen, so these are mutually exclusive. So we just have to add the probability of a king plus the probability of getting a queen. So there's 4 of those, so 4 out of 52 and 4 out of 52. So we get 8 out of 52, or divide that by 4, we get 2/13. So those are OR conditions. Again, we're adding the probabilities, but you have to consider whether they are mutually exclusive. Now, sometimes it's impossible to list out all of the possible outcomes of something. So there is a multiplication counting principle that we can use here. In the second part of this, we'll be going into more elaborate counting techniques. But essentially, if we have m ways here to make a first selection and then n ways to make a second selection, the total ways of making the pair would be m times n. And if we have 3, 4, or 5 different selections, we could continue. So we'll look at a couple examples here. You're choosing an outfit to wear. That should be an outfit, not an, sorry. And you've got 5 different pairs of jeans and 6 different t-shirts. How many can you make? Well, we can pick from 5. We can choose from 5 pairs of jeans and 6 different shirts, so 5 times 6 is 30. So let's look at this example here that's a little bit more complicated. So we're trying to figure out how many different telephone numbers there could be with these set of rules. So we're going to be picking 7 digits, so let's make 7 spaces here. And So our first digit, it says the digit cannot be a 0 or 1. Now the digits are 0, 1, 2, 3, up to 9, so there are 10 digits. And for the first digit, we can't use 0 or 1, so there's 8 total digits. There's no restriction here, so we could have 10 digits, 10 digits, 10 digits, 10, 10, and then it says the last digit cannot be a 9, so we only have a choice of 9. So to find the total number of telephone numbers, we would multiply this together, and we're going to get 72, and then we've got 1, 2, 3, 4, 5 zeros. So there would be 7,200,000 different telephone numbers that we could create. Okay, our last topic here on probability is going to be AND events. So we're going to be doing say two things, selecting two objects, flipping two coins, etc., and we want to know the probability of a combination of the events. In this case, we need to, when we look at the formulas, decide whether the events are independent of each other, meaning can the outcome of the first event affect what happens on the second. If the two events are, if the first event cannot affect the outcome of the second event, they are called independent. And if the first event can affect what happens on the second, then they are called dependent. So if you're flipping two coins or 5 coins or 10 coins, those are independent because the flip on each coin does not affect another one. Rolling two dice, what happens on the first dice does not affect the second one. When we're selecting objects from, say, a bag or a jar, it depends on whether or not we are replacing the object after the first draw. If after each draw we look at it and decide did we get the outcome we're looking for and then put it back in, the events are independent. If we pull out multiple objects without replacing them, then they are called dependent events. So let's look at an example here. Well, first the formula. So if you know two events are independent, then the probability of both events happening, we multiply the two probabilities together. If you know that the two things are dependent, then we're still going to multiply the probabilities, but we don't multiply by the probability of just B, but we have to multiply by the probability of B knowing or given, that's what this symbol means, that A did happen. So the classic problems on these are selecting marbles from a bag. And how you know if they're independent or dependent depends on replacement. If we draw a marble from the bag, we look at it and decide success or failure, and then put the marble back, shake it up into the bag, and draw again, those are independent. So with replacement is independent. So the probability in this bag, so our bag has 10 marbles, 4 red, 5 blue, and 1 yellow. The probability of getting a red and a blue marble, so the probability of getting a red is 4/10. Now again, that red marble is put back into the bag and shaken up, so there's still 10 marbles in the bag and this mixture. So the probability of blue is 5/10. We multiply those probabilities, so we get 0.2. The probability of getting a red followed by a red would be 4/10 times 4/10. And the probability of yellow followed by yellow is 1/100th. Now it's possible to get two yellows because remember, we draw the first yellow, look at it, record it, and then put it back into the bag, so there's still a yellow one. Now let's look at what happens when we are not replacing. So let's look at the same set of events. So when we get the probability of a red followed by blue, we assume success. So on the probability of red, that was 4/10. Now for the second, we assume we're holding a red marble. So there are only 9 marbles in the bag, and now there are 3 red, 5 blue, and 1 yellow. So there's still 5 blue. So we get 5/9 on this part of here, the probability of blue given that it was red. Multiply those probabilities. So again, we get different probabilities, sometimes greater, sometimes less when we have the dependent events. Probability of a red followed by a red. Well, the first draw, there are 4 reds out of 10. Now we're holding one of the reds. So there's 9 marbles in the bag, and we're holding a red one, so there's only 3 red left. Again, we multiply those together. The probability of getting 2 yellows, you probably can understand, is going to be impossible because on our first draw, there's a 1 out of 10 chance, but now we assume success here, so we're holding a yellow marble. There's none left in the bag out of the 9 marbles, so we get 0/9, so we get 0 over 90 when we multiply, or a 0 probability. So good luck working the problems on the probability, and talk to you for the next unit, which will be on counting principles.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready?